Hello everyone, I am Eshan Tripathi, Physics faculty at askIITians, and today we're going to start with another chapter of Class 9 Physics, which is work, energy, and power. So, work, energy, power, very interesting topic. Like in the series of the chapters that we have learned in mechanics, we first learned motion, then we learned laws of motion, governing the forces, which talked about how the motion is going to be. And now we are proceeding to the next chapter, which is work, energy, and power. Very interesting and very important topic, especially from Olympiad's point of view also. Because in Olympiads, many of the topics would be clubbed, like many of the topics from motion and laws of motion will be clubbed with this work energy to frame very interesting problems. So let's start with it without wasting the time. So basically in this chapter, in this lesson, I'm going to talk about, I'll introduce you guys to the concept of work, and then we will talk about work done by a constant force. Okay, we'll look into that later. But first, let me tell you what work is. What is work? So, if you can see, like the picture that you have of work in your mind is you're doing some work, so that means you're getting tired. Basically, you're putting in some effort. Like you could also use the word effort to describe the meaning of work that you have in your minds. So, you would say if a person is weightlifting, he's putting in efforts, he's getting tired with time. So, he must be doing some work. That's fine. Like that we can agree for once, but that does not seem to be correct in physics if we talk about work done by this guy who's trying to push a wall. What would you say? When this man is pushing a wall, the wall is not moving. Do you think he has done work? It won't be called that it has done work according to physics. Now, if in everyday life anybody could say both of these men are getting tired, this guy also and this guy also is getting tired. True. But that is not the meaning of work in physics. In physics, work is a bit different from this. It is defined as a bit different from this. So, if you want to understand exact meaning of work in physics, I would suggest do not think about the meaning of work in everyday life that you have in your mind. Try not to relate with it right now. Otherwise, it will become very complex. So, don't think about it. First, let's see what is work and what is required to do work. What do you think? What is the main thing that must be required to do the work that I'm saying this man is doing? And that is force. Unless somebody does not apply force, no work will be done. Right. So let us see how exactly the work is defined in physics. Work in physics is a measure of energy transfer that occurs when something is moved or displaced by an external force, or at least part of which is applied in the direction of displacement. So this at least part we'll be studying later on. But yeah, for now, work in physics is the kind of measure of energy that you're transferring. So this way, I think you will be able to relate more with the previous two images. Is this person transferring any energy to this weight that he's lifting? Yeah, seems like he's pushing and pulling it up. So, like pulling it down, pulling it up. So it might seem like, okay, some energy is being transferred to this weight. But is this guy transferring any energy to this wall? No, the wall isn't even moving. Nothing is happening to the wall. So one could say that no work is being done by this guy because it's something to do with energy. Okay, but what exactly is energy? Also, we're going to study later on. But I think you're getting a little bit idea right now what work could be. Like it's kind of transfer of energy from one body to other when it is this when the other body is displaced. That too, as it's mentioned over here, um, at least part of which is applied in the direction of displacement. What that means, we'll study in the next page. So for now, let us move to the work done by a constant force. What is that equal to? So we are going to imagine work as the mathematical quantity that we have learned earlier, which is called dot product. In the beginning of the session, we learned dot product of two vectors. So if there is a vector f and there is another vector d, so work done is defined as the dot product of force vector and the displacement vector. This is what work is defined as. So if you guys don't remember what work done was, let me tell you. sorry, if I talk about dot product, so if there are two vectors, let's say A vector over here and B vector over there, and they have an angle theta between them. So according to the definition of work, sorry, according to the definition of dot product, A vector's dot product with B vector, this was defined as the magnitude of A vector, then the magnitude of B vector, and cos of angle between them theta. This is how dot product of two vectors was defined. Okay, so don't think about work right now. Just think about this. What is dot product of two vectors? There is one vector A, another vector B, and they have some angle between them, theta. So the dot product of A and B is defined as magnitude of A, magnitude of B, and cos of angle between them. Okay. So now let's try to relate this. What we are saying is work is also defined in the same way. In fact, for us, dot product is defined in vectors to actually talk about work done. Work done is dot product of force that is acting on a body, dot product with the displacement of the body. Displacement force both are vectors. Let me give you a little bit of idea. Um, let us say there's this ground, there is a block, and mass of let's say that the block is very heavy, and there is a guy who's trying to push this. So there's a guy present over here trying to push this block towards right. So he needs to apply some force to push this. So he would apply a force F, or let's give it a value, 20 newtons. He's applying 20 Newton force towards right. So now what will happen because of this force that he's applying? If the ground is smooth, there is no friction. Let us say there is no friction. So this block would start slipping towards right. If the ground is smooth, it will keep on moving towards right. And overall, with this 20 Newton force, it would keep on getting accelerated. And eventually, it would have undergone some displacement. Let us say it got displaced by a distance of 4 meters. Okay, if you are applying a force of 20 newtons and this block got displaced by 4 meters towards right. So the question is, according to this definition of work, a very mathematical definition, I agree. Don't think about the physical meaning of it. I'll convey that to you. But for now, work is defined as dot product of this force vector, 20 newtons, and displacement vector, 4 meters. So what do you think should the work done be? So it's the dot product of these two vectors. So it would be the magnitude of first vector, force, which is 20, then magnitude of other vector, which is displacement d, which is 4, cos of angle between them, because it's cos theta. F dot d is going to be f d cos theta. So what should be the angle between these two vectors? F vector, force vector, 20 Newton towards right, and displacement vector, 4 meters towards right. Since both are towards right, they are in the same direction. So they have no angle between them. They have zero angle between them. So it would be 20 multiplied by 4 multiplied by cos 0 degree, which is 1. That this gives us 80. And what's your guess? What is the SI unit of this? 20 is in newtons, displacement is in meters. So shouldn't its SI units be Newton meter? Right. But we just love to give new units in physics. So Newton multiplied by meter, let's give it a new name. And this would from now onwards be called 80 joules. So SI unit of work is joules. SI unit is joules. And that is how we define work. Work, not define, sorry. This is how we calculate work. 20 newtons of force was acting over 4 meter displacement. So the man has done 80 joules of work. This is how we are going to find work done by a constant force. Okay. So with this, let's proceed to the next thing. Work now is a scalar quantity because it's a dot product. It does not have any direction. It's just F dot D. It's magnitude of F, magnitude of D, and a trigonometric ratio. So it's just a number, it's scalar. And that is why, guys, if you recall, dot product was also called scalar product. Remember that. It was taught in the beginning. Dot product is also called scalar product. Reason being, its resultant is a scalar quantity. It's just a number. But although it's just a number, it does not have any direction. but it still can be positive or negative. A number can be positive or negative, except for example, temperature. Temperature is scalar or vector. It's scalar, it does not have any direction. But still temperature can be positive also and negative also. So quantities, scalar quantities can be positive, negative both. So can work also be positive or negative? Yes. So first we're going to talk about positive work done. So it says whenever force and displacement are in same direction, the work done on an object is positive. Let's see. Work, as we said, is F into D into cos theta. Wait, now cos theta. F is always positive. FD is also always positive. Force would always be, it's a magnitude of force, always positive. Magnitude of displacement, always positive. But it's only cos theta which can be both positive and negative. So guys, cos theta is positive for which values? Cos theta is positive when theta is between 0 degree, and I should not put equal to sign, when it's between 0 degree and 90 degree. At that time, like basically as long as theta is acute, the angle between them is acute, it's going to be positive work done. Let's draw some pictures to understand this. For example, like in the previous example what we did, there is an object moving towards right. So as long as the man is pushing it like this, let's say 80 newtons of, or 80, how much was the force that we applied? 20, 20, 20. Okay. 20 newtons of force was applied to cause a 4 meters displacement. So how much will be the work done by the man? That's positive 80 joules. Reason being, angle between them was 0 degrees, an acute angle. Positive work was, this was the case of positive work. Okay. For example, in this case also, when this man is trying to lift this object, weight of the object is moving, is acting downwards, fine. But in which direction is the man applying the force? To lift this body up, man would be pulling it up with some force F. So he's applying force in the upward direction, the man. And displacement of the body is also upwards. The body was lifted up. Force displacement in same direction, positive work is being done. I'll explain the physical meaning of this also. But yeah, this is how your understanding of positive and negative is there. And similarly, there can be negative work done also. You can imagine that. Because cos theta is negative for theta being from 90 degree to theta going to 180 degree. Like if the angle is obtuse between force and displacement, then it's going to be negative work done. Let us see how that can be. Like you can pick up this example. Um, yeah, the same man we had earlier, who the same guy is applying force. Now he was pushing it with 20 newtons of force, and block got displaced by 4 meters. We have already found out his work done. But now imagine if there was another boy who was trying to push it back. He does not want this block to move towards right. So he is pushing it towards left, let's say with a force of 5 newtons. So left person is a man, right person is a boy. So the work done by man we have already found out. Work done by man is 20 times 4 times cos of 0 degree. Because man was pushing towards right, displacement towards right, same direction, 0 degree angle between them. So that's plus 80 joules. The man did positive 80 joules of work. But the question is, what is the work done by the boy over here who's trying to oppose it? So look at it. The boy is pushing it towards left with 5 newtons, but the displacement of the body is 4 meters towards right. So work done is going to be the force applied by boy multiplied by displacement of the block and cos of angle between them. I know you guys might have some questions over here, but this is second. I'll address them. 5 Newton force towards left, 4 Newtons of 4 meters of displacement towards right. So what is the angle between these two forces? These two vectors? That is 180 degree. So we know cos 180 degree is -1, so it would be minus 20 joules of work. So now the question that you had in mind was, this man is pushing it towards left. Why would it displace it towards right? These two things are happening at the same time. The blue man is pushing it towards right, so he does positive 80 joules of work. But the red boy is trying to push it towards left, so he does negative 20 joules of work. Overall, it moves towards right because man has done more positive work. Okay, so let me explain to you the physical meaning of positive and negative works done. Here, positive work means that the effort of the person, like the force, or I can say, see, work is a measure of kind of effort that he's putting in that we discussed in the beginning. So if he's putting in the efforts or the force that he's applying, if it's stimulating the motion, stimulating the displacement, I should say, then the work done by that force should be positive. And if the work done is negative, if negative work is there, then the force is not stimulating the displacement, the force is opposing the displacement. So getting this, guys, this man over here, he was applying a force that could cause this 4 meters displacement. So he is a factor which is causing that displacement. So he does positive work. He's contributing to it. 20 joules is causing this force. So that's positive 80. But this man with, sorry, this boy with 5 Newton force in the opposite direction, he was not trying to stimulate it. He was not trying to cause it, but in fact, he was trying to oppose it. So his work would be negative. He's doing negative work over here, trying to even oppose that. Okay. So for example, in this case, like this is the same picture as in the previous slide, but earlier we were talking about work done by the boy in lifting it up. That was positive because boy is pushing it up to cause the displacement upwards, same direction. Who is doing negative work over here? Who is doing negative work in this case? You would say W. What exactly? Who is applying that W? W is weight of the body, basically gravitational force exerted on the body by the earth. So work done by the earth in this case is negative. Earth is doing negative work. Earth did not want that this body should move up. The earth was trying to oppose it. So earth did negative work. Earth was trying to oppose it. Boy did positive work because he was trying to lift. So that's the difference between positive and negative work. I hope that's clear. But now you would think for 0 to 90 degree positive, 90 to 180 negative. So what exactly happens at 90 degree? Whenever theta is 90 degree, you know cos theta is 0. That means no work is done. Like whenever force vector and displacement vector are perpendicular to each other, no work is done by the force. Just look at this case. This man, sorry, no, let's not look at the man. The man is trying to move it, like he's trying to displace it towards right, displace the block towards right, or this box towards right. But when this force, let's look at the force exerted by the earth. Earth is trying to pull it downwards. Earth is trying to pull it downwards, and the body displaced towards right. So tell me, don't think about anything else. Just think about Earth and this displacement. So when the block is moving towards right, is Earth responsible to cause this displacement? No, it's not causing this displacement. Is it trying to oppose this displacement? No, it's not even opposing it. So it's not trying to stimulate it. It's not trying to oppose it. It has no contribution towards this displacement. That means work done by Earth in this case is 0 because theta is equal to 0. Sorry, theta equals to 90 degree. And similarly, in the third case also, work done by the centripetal force is zero. Why? Because in swinging, displacement is always tangential in a circle, and force is always towards the center perpendicular. Again, theta is 90 degree, work done is zero. So when angle is 90 degree, then work done is zero. In which other case can work done be zero? Like in the first case, this man is doing no work. As we discussed in the very first slide, if you remember, we said this man is not doing any work. Why? Because although he is applying force, the displacement in the first place is zero. So why would there ever be F dot D? Work done will be zero. So if he's applying a force, putting in efforts, but still displacement is not taking place. Physics wise, no work is done. Okay. So that is how we define work. We have talked about the mathematical thing of it. After this, let's do a question. A body has mass 3 kgs. A body has a mass of 3 kgs, which when applied with a force of 8 newtons, moves from rest with a coefficient of kinetic friction zero point 0.2. So you have to find these three things. So let me draw the question over here. There is a body of mass 3 kgs, and on it has been applied a force of 8 newtons. The body is originally at rest. The coefficient of kinetic friction from the ground, of course, is zero point 0.2. Coefficient of kinetic friction is 0.2 units. The question asked is, when this force is applied for 10 seconds, what is the amount of work done? Now see, coefficient of static friction is not given. So I'm assuming that definitely the block must already be slipping. Like coefficient of static friction must be small only. Okay. So let's see. Coefficient of kinetic friction is given 0 0.2. So what are the forces acting on this body? Let's draw the free body diagram. The free body diagram of this block as learned in previous chapters. How to draw free body diagram? You know that from laws of motion. So free body diagram means all the forces must be all. We have to draw all the forces which are acting on this body. So one force is going to be the weight of the body, mg, which is in this case 3 kg is the mass. Let's assume g to be 10 meters per second square since it's not given. Okay, so it's going to be 30 newtons of weight is acting on the body downwards. Other than this, since it's kept on ground, a normal reaction must be acting upwards. So let's draw that normal reaction from ground ng. How much should that be? Okay, let's do it in the end. Then what other forces are acting? One more force is acting towards right, which is 8 newtons, which we applied from outside. And lastly, one more force is acting, which is friction. So friction will be acting leftwards, which is equal to mu k into normal reaction from ground. Yeah, mu k into it. Now let's see. Overall, is this block in equilibrium? No, no, no. We do know it's already slipping. It should not be in equilibrium. So it is accelerating towards right. Everyone can imagine that. But it is accelerating towards right. So can I say along vertical, it is in equilibrium because there is no acceleration along the vertical direction, upwards, downwards. So along vertical, it's in equilibrium. And I can say upward force is equal to downward force. Normal reaction from ground is downward force, which is 30 newtons. So that is one thing that I've got. Normal reaction from ground is 30 newtons. Okay, let's write newtons also. Yeah, units. And now let's study the motion along horizontal. So along horizontal, is there any net force acting along horizontal? Yes. 8 Newton force is acting towards right, but there's a friction towards left that is mu k into normal reaction. Mu k is 0 0.2, normal reaction is 30 newtons. So I think the kinetic friction acting is 6 newtons towards left. So what is the net force towards right? F net should be equal to ma. What is the net force towards right? Net force is 8 minus 6. 8 newtons towards right, external force, 6 friction leftwards. That is equal to mass of the block, which is 3 into acceleration. That means acceleration of the body is 2 by 3 meters per second square. That is the acceleration of the body. Why have we found acceleration? Okay, let's see. because we wanted to find the work done in 10 seconds. In 10 seconds, if we have been fast the force so we know, but we also need to find the displacement in this time. Otherwise, how will we be able to find the work done? So since we wanted to find out displacement, we found out the acceleration. Now let's start with the A part. For the A part, you need to know the displacement of the body. So for displacement, we already know the third equation of, sorry, not the third, time is given. We can use the second equation of motion. Yeah. According to second equation of motion, displacement S is equal to ut plus half at square. Initial velocity, 0. Into time, doesn't matter. Plus half into acceleration. Acceleration is 2 by 3 into time square. And time is given to be 10. So that comes out to be 100 by 3 meters. So in 10 seconds, because these two forces were acting 8 Newton, 6 Newton, acceleration was 2 by 3. And overall, it got displaced by 100 by 3 meters towards right in 10 seconds. So the first question, the A part of the question was, what is the work done by this external force? Okay, the work done by the external force is going to be, work done by this force F is going to be that external force itself. Its dot product with displacement. We have called it S in this case. Cos of angle between them. What's the angle between the force 8 newtons and displacement 100 by 3? Both are towards right. So angle should be 0 degrees. So Fs cos 0 degree, which is 8 times 100 by 3 times cos of 0 degree, which is 1. So this gives us positive 800 by 3 joules. That is the first answer. Work done by this external force. Second question is, what is the work done by friction? Okay, let me use some different color. Work done by friction. If they're asking work done by friction, that should be the friction force multiplied by displacement, cos of angle between them. But in this case, what is the angle between friction and displacement? Friction is towards left, as you can see over here. Friction is towards left. Displacement is towards right. Friction is trying to oppose it. So it would be, and angle between them would be 180 degrees. So it's going to be the magnitude of the force, friction force, which is 6, into displacement, which is again 100 by 3. But angle between them is 180, so cos 180 degrees minus 1. So that's minus 600 by 3. That comes out to be minus 200 joules. Okay, simple. The friction has done negative work because it is trying to oppose it, of course. And then the last question is, what is the net work done? So guys, net work done in this case would be the sum of these. The work done by capital F plus work done by friction small f. That is 800 by 3 minus 200. That is 200 by 3 joules positive. So net work done is this. So that's how this question goes. After this, we can move to the next question also. Now let's see. It's a little bit less mathematical. A 1200 kg car and 2400 kg car are lifted to the same height at constant speed in an auto service station. Lifting the more massive car requires more work, less work, twice the same, 4 times the as much as the work done in the lighter one, or equal to 4 times as much. So let's see how to do this. Now, important thing to notice over here is they are being lifted through same height at constant speed. Constant speed. If speed is constant, what is the value of acceleration? 0. That means what must be the net force acting on the body? Again, 0. Body with constant speed, the body should be in equilibrium for sure. Both the cars are being lifted up in equilibrium. Remember from the discussion of Newton's laws of motion, equilibrium does not mean body is not moving. All equilibrium means is forces are balanced, speed is not changing. If it has some speed, it will remain constant. Okay, so let us see. We are saying there is this car. Let me draw a car. Okay, pretty close to reality. Wait, not at all. So let's see. There is weight acting on the body on the car mg. The earth is trying to pull it down with mg force. But at the same time, if you're trying to pull it up with some force F, we're trying to pull this body up and it is in equilibrium. How much force should we apply so that the body gets lifted up in equilibrium? Mg only. Exactly equal to mg we need to apply force so that the body stays in equilibrium. So equilibrium, again, I'm telling you, does not mean body is at rest. Equilibrium means it's not speeding up or speeding down. Car was already moving up with some speed. Since we are balancing the forces, it continues to move with constant speed. It does not accelerate suddenly. Okay. So it is moving with some constant speed, and we are applying mg amount of force to lift it up. Now let us say it is lifted through a height h. How much is the work done by us? Work done by the external force. What is the external force in this case in lifting it up? The external force is this F, which is equal to mg in this case, and causing a displacement of h. Both are upwards. How much must be the work done? It should be mg multiplied by displacement h multiplied by cos of angle between them, which is 0 degrees. Okay, wrong pen. But yeah, it will come out to be positive mgh. So in lifting one particular car of mass m to a height h, positive mgh amount of work needs to be done. Now we are saying the other car is also lifted through same height, but its mass is double. So if we double this mass m, what do you think? How many times will work change? The work will also become double now because work is directly proportional to m from this relation. So the answer is C, twice as much. And after this, I hope this is clear. Let's move to the last question, which requires more work. Lifting 50 kg crate through a vertical distance of 2 meters or lifting 25 kg crate through a vertical distance of 40 meters. Again, very similar. There is a block or crate of mass m. Mg is the gravitational force acting. If you want to lift it up, let's again assuming it's moving very, very slowly. So we are applying a force F almost equal to mg only. And it is lifted through a height h. So again, the work done by this external force will be positive mgh. If you are lifting it up, you are the one causing displacement. You must be doing positive work. So in the first case, in the case one, it has been said mass is 50 kgs and displacement h is 2 meters. So guys, what will be the work done in case one? That is going to be 50 multiplied by g, which is 10, multiplied by height, which is 2. That gives us 1000. Positive 1000 joules is the amount of work done in the first case. Right now. Now let's talk about second case. The mass in the second case is half of it, 25. But height through which it is lifted is double, 4 meters. Alright, it's so simple. Mass 25 multiplied by g, which is 10, multiplied by height to which is lifted 4, which again comes out to be 1000 joules only. Although the mass halved, displacement also doubled. So both required equal amount of work. So that is it about work. And in the subsequent lecture, we will study what kinetic energy is and then a very interesting theorem, which is work energy theorem. So let's see that in the next lecture. For now, this is all we have from work and work done by constant force. Thank you, guys.